so then the clock field is diffeomorphism invariant because it's located on a single. After we fix the gauge, it's on a certain time slice, right?
No, the clock field is not gauge invariant. The Dirac observable is gauge invariant. This quantity is gauge invariant.
Okay. So then, how to understand this clock field depends on. So okay, so if we set this t at the capital Tx equals to tau, and this is the thing, and we pick up this time slice, and then it still depends on location. So then in this.
No, it's not dependent on location. So it's suppose. So here you understand you fix tau and sigma as a number. So this is this sigma, this qij tau sigma is a phase-based function only when tau and sigma is a number. Say you say tau equals to 0, sigma equals to 0, then this guy is a number, right? But this number depends on phase-based variables. It's on Q.
I see.
So this guy is a function. So this guy is a functions. So this qij tau sigma are functions on phase space parameterized by tau and sigma. So which means that you have to put in numbers, tau equals 1, sigma equals 1, then you get one function. Yeah? And this function is gauge invariant.
Okay, so is this Brown-Kukash-Dast action diffeomorphism invariant?
On the action, you mean action itself?
Yeah.
Yeah, the action is always diffeomorphism invariant because it's integral over the space-time. So the action is diffeomorphism invariant.
So, but now we can talk about this total action as locally, and it has an energy density.
No. So the total action still has no local energy because the Hamiltonian, well, the gravity coupled to matter, the Hamiltonian still a linear combination of constraints. Okay. You can talk about energy. You can talk about Hamiltonian only when you come to the reduced phase space. You cannot. So I'm hesitating to call that Hamiltonian energy. Because that is a so I'm more it's better to call that Hamiltonian a generator of the tau evolution. Yeah. So that Hamiltonian is completely different from this Hamiltonian. This Hamiltonian, the usual Hamiltonian. This is the standard Hamiltonian for gravity coupled to dust. When you do the Hamiltonian analysis, and this is still a linear combination of constraint and still 0 on the constraint surface. Yeah. Okay, and over there, what you do actually, you find a way to make gauge fixing, or you find a way to introduce some parameters tau and sigma, which has physical meaning. It has physical time and physical space, and because they are value of dust field, you can use those tau and sigma to parameterize your field. And then you ask the question if you can extract the Hamiltonian to generate this tau evolution. You consider tau, a specific tau, to be your time, to be time. Okay, and you ask question whether you can find the Hamiltonian to generate this tau. The answer is yes, you can find the Hamiltonian to generate this tau. But to really call this Hamiltonian to be energy, well, it is. You need to hesitate because apparently this Hamiltonian depend on the coordinate. It depends on tau coordinate. Yeah. So and it rely on the specific choice of parameterization using dust. So I think usually we don't call that an energy. It is a better called physical Hamiltonian. So the relation, at least I'm not completely clear. I'm not completely convinced that this relates to certain kind of energy, but maybe.
But it's just physically hard to understand that if the space-time is coupled with matter, then then we should have energy density, right?
No, no, we don't. No, we don't. So it is the non-locality of the gravity. So whenever anything coupled to gravity, you don't have local notion of energy anymore.
Okay.
So I mean, before we did Hamiltonian analysis for pure gravity, but suppose you do gravity coupled to whatever kind of matter, you still don't have. It's still a general covariant system, and in the end, you still don't have a local notion of energy.
Oh, I see.
Hamiltonian zero all the time because the system is diffeomorphism invariant.
Okay.
No matter gravity or gravity coupled matter. Okay.
Okay. Okay.
All right. Is there any other question? Okay. If not, let's stop. So I think this series of lecture is going to finish. I'm going to finish everything. So I think next time I'm going to talk about semi-classical analysis. Well, let's say hopefully I can finish all the lecture by the end of this week. So which means hopefully we only have one lecture. So next time I'm going to talk about semi-classical states, and I'm also going to talk about talk a little bit about black hole entropy counting in the next lecture, because that's something interesting as well. Yeah, and then we just finish everything. Yeah. So probably we only have one lecture left for the entire series. Okay, so see you next time.
Okay, thank you.
See you.
Thank you.